Okay, so let's kind of go through each of these sections on the left. Make sure everybody's cool with what I want. So, on the first part, you started off, here's this block of wood. You pulled it at a constant velocity, okay? The two most important words there is that you are at a constant velocity, which means all the forces add up to zero. So there's two ways in which an object
We got the same answer.
can have a constant velocity, okay? And it's important that you understand the differentiation between the two of these two. Option number one, you have to overcome the gravity mafia or some opposing force, and your applied force is just balancing that out, okay? So that's option number one. That's most of your reality, okay? When you set the cruise control in your car at 55 miles an hour, whatever that is, basically you're telling your car to apply a force that is balancing out the opposing forces in the opposite direction. So from a physics perspective, cruise control means the system's in equilibrium, all your forces add up to equal to zero. Okay, that's what cruise control means from a physics perspective. So when you pulled that force, I don't know, let's say it was 0.90 newtons, okay? That was your applied force. That's how much force it took to move it at a constant velocity. What that means is that that frictional force is negative 0.90 newtons, okay? And this, again, this is not Newton's third law, okay? This is not Newton's third law. All this is saying is that this system is in equilibrium. Where Newton's third law plays in is that when you took that and you hooked it up to the hook, that would be Newton's third law, where you're applying a force to the hook is applying an equal and opposite force back to the spring, okay? That's where that would work, okay? This is just adding all the forces add up to equal to zero, okay? Then you've got Fg, and you have your force normal. So that first diagram is going to look something like this. It's going to look like a big plus sign, okay? Make sure I know what the scale is. Make sure that you have labeled your vectors, okay? Because if you just draw vectors, I don't know what they are, that has no meaning to me, okay? Great, I see vectors. Fantastic. You can draw arrows. I don't know what that means, okay? The second thing you're going to do is you're going to draw that tip to tail. I always draw my normal or my gravitational force first, and then my force applied. Here's my force normal. There's my force friction. And again, every force problem that you're going to work can only play out one of two ways. Either the forces end up back at the origin, and you're at a constant velocity, and that constant velocity might be 0 meters per second, it might be 10 meters per second, it might be negative 20 meters per second. So if you have a constant velocity, when you add up all those vectors graphically, you end up back at the origin. If they don't end up back at the origin, that means you're going to accelerate. Okay? Now, when you get to that part B, you added more and more mass to the block. You're going to draw a graph where you're going to have force friction here, you're going to have force normal here, you're going to have some data points, you're going to have a line of best fit. Notice that I tell you to circle the points and write the coordinates on the graph, okay? So I want to see which points you pick, because everybody's going to be a little bit different. Pop?
So force friction is not negative then?
No, because it's an absolute value. If you made it negative, that's fine.
So if on my graph it's negative. Because force friction is the opposite of the force applied, right?
Yeah.
So it'd technically be negative. So
That's fine.
that's fine.
Yeah.
But then the thing is the slope is negative.
But
And
you're
the
finding
slope
the
represents
coefficient
the
of friction.
coefficient, so
Yeah.
can I just change the slope to positive?
Yeah, that's fine.
Okay, thank you.
Main point being is that you have the graph. That's
Yeah.
what I want you to
Oh,
see.
okay.
Yeah, you're fine. Okay, now, let's talk about, so is everybody cool with that? Now, when you answer question number 6, okay, notice I tell you, explain in terms of acceleration. Guess what word you should have in your answer to number 6? Acceleration. Okay? If you don't have acceleration in your answer to number 6, just don't write it at the end and go acceleration. Okay? It's not the point. Okay. Now, let's talk about number 7. So on number 7, here's what I want you to see. Here's this car. You have gravity acting on it. You have your force normal. Okay? Now, so here's the car, right? So imagine here's the car. You've hit the brakes. When you hit the brakes and this car is still moving, what are the 3 forces acting on that car? Friction, gravity,
Force.
and the normal force, right? The road bed is keeping it from falling down, right? So you have 3 forces. So if the car is going in this direction, your frictional force is acting in the opposite direction. Okay? Now, so at this point, here's what I want you to see in terms of the difference. When you were pulling the block at a constant velocity, all the forces add up to equal to 0. And you were moving at a constant velocity. Draw it tip to tail, ends up back to the origin. If this car is going to accelerate, that means your forces can't add up to 0. So when you have an accelerated motion, when you draw them, there has to be some unbalanced force. And this is what we're going to call a net force eventually. Okay? So here's what I want you to see. When you have that value over there, notice that there's no force acting forward. Okay? Do not think, I want you to get this out of your minds right now. Inertia is not a force, okay? Inertia is the tendency of an object to maintain whatever state of motion that it's in. So when I let go of this, there is no force making it go forward, okay? Does it have inertia? Yeah. Does it want to keep moving forward? Yes. But inertia is not a force, okay? I cannot emphasize this enough. Inertia is not a force. It's a tendency of an object that has mass to maintain a straight line path at a constant speed. So when I flip this over and go with the wheels, I don't change the amount of inertia, okay? It still has the same inertia whether I do it with the wheel sides down or if I flip it over. It's still the same amount of inertia. The difference being is that if I do this upside down, now there's a lot more frictional force that's going to make it slow down. If I do it with the wheel sides up, it's still the exact same inertia. I just don't have that as much frictional force to slow it down as quickly. So what I want you to see on number 7 is that I've given you mu, and you know that mu times force normal equals force friction. Now, this has to be a force, right? And force normal is the same as Fg. Technically, there's a cosine theta part on there. We don't have to worry about that because we're still on a flat surface, okay? And that's going to be mg. Now, do not worry, do not get hung up on signs and worry about signs. Here's the best advice I can give you. Just take mass times your gravitational acceleration, get the weight, make that the normal force. Multiply that by mu, keep everything positive, okay? Just get a number. Then look at the problem and decide, hey, is this frictional force going to be a positive or negative value, okay? So look at it this way. You're moving at 10 meters per second. This car is moving with a positive velocity in this direction. Which direction is my frictional force going to act?
Negative.
The opposite direction, so I'm going to make that frictional force a negative value, okay? So mathematically, your frictional force doesn't work out to be a negative value. But you have to look at it in the context of the problem and go, wow, I have positive velocity. This car is going to slow down. I've got to have negative acceleration. The only way I can have negative acceleration is if I have a negative force acting on the car. So get the number. Look at that. Oh, I got positive velocity. I'm slowing down. I've got to have a negative force. Okay? So that's why I said just get the number. Look at the context of the problem, decide if it makes sense to keep it positive, or do I need to make it negative, depending upon the physical situation of the problem. Okay? Now, over there on page 2, okay? So, if 8A is wrong, or if that acceleration is wrong, everything else is going to be wrong. So, your acceleration on 8A should be around like -5. Okay? If that's wrong, everything is going to be wrong. So, any force can also be written as mass times acceleration. So, that frictional force is what's making this car slow down. So, to get your force friction, you have the acceleration, multiply that by the mass, boom, there's your frictional force. Okay? So that frictional force should be in the mid-5,000s. Okay? Kind of an ish, but it should be in the mid-5,000s. Now, let's talk about mu. I'm going to show you a little bit of a shortcut if you want to take advantage of it. If you solve for mu, that's force friction over force normal. So force friction in this situation is mass times acceleration. Force normal is the same as your weight, which is mg. So if you want to get fancy, mu is also the ratio of the accelerations. Okay? Because force friction is the same as mass times acceleration. Force normal is the same as your weight, which is mg. The masses cancel out. So on that one, when you find mu, the easiest thing to do is just take that acceleration and divide it by 9.8 meters per second squared. Boom, there's your value of mu. Okay? So that's why if you look at this in terms of variables, you can a lot of times see hidden relationships that are there. It's like, oh, I can just cancel out those m's. It's just a ratio of accelerations. Okay? There you go. Your answer to number 9 would make a horrible GPA. Okay? Horrible GPA. On number station 2 with the equilibrium part, okay? With that one, you're going to add them the tip-to-tail method. So a number that one, you should have something like vector A, and this is going to vary greatly depending on how you set this up. Vector B and vector C. In an ideal world, your vectors are going to end up exactly where you started. In reality, you might be off by a little bit. Okay, draw it as it is. Now, if you do this and you end up way out there, that's a train wreck. Okay, something has gone horribly wrong. But they should theoretically pretty much end up back at the origin. Louis?
Did we already go over number 10?
Oh yeah, can we go over number 10?
Number 10 was a little bit confusing.
3 ways to determine the numeric value of mu?
Mhm.
Yeah.
Okay.
I understand like how to do it. I just don't know which ones.
Hold on, just hold on. I'm going to get you through this. Okay. So at the very beginning of the lab, that very first part, when you were pulling it, when you were measuring the applied force, what were you measuring?
Force friction over force.
No. You were just the applied force was balancing out the force friction.
Okay, yeah.
So one option is that you just pull it at a constant velocity. However much force it takes is whatever the frictional force is.
And F equals everything.
F equals ma, and then look what you just did.
Mu times force normal.
There you go.
Oh, okay.
So how would we write out the first one? Where we
Just say
pull at constant.
pull at constant velocity, and then your force applied is equal to your force friction. So the other way that you can have constant velocity is if there's just no opposing forces at all. Like if you're in deep space, you give something a push, it's just going to maintain that constant velocity because of inertia. But almost every situation that we're going to be in, you have to have an applied force to balance out that frictional force. Because unless I specifically tell you otherwise, you're always going to have 2 mafias to deal with. The frictional mafia and the gravity mafia. Go with that one.
Good.
Okay. Now, let's talk about that third one with the cart.
But
What?
what about number 6 on the equilibrium one? Do we have to like calculate an exact angle, or is it just an estimate?
No, you should have you don't have to calculate it, but if you look at your data, you can pretty easily figure it out.
Like around where, or
No, it should be an exact number.
You do the like.
It's the inverse.
oh no? Oh, okay.
So,
Yeah.
Good?
Yeah. Good.
Okay. All right. So let's talk about the cart. And I promise you, you're going to have problems like this on the test. I promise you. So this is kind of like one of the standards of all of physics. Okay, so let's say you start with that 10-gram mass. Okay, so let's go through this dynamic. That 10-gram mass weighs 0.098 newtons. Okay? So here's what I want you to see. You have a downward force acting on this thing is 0.098 newtons. Situation number 1, I just cut that string. Just cut it. I'm not dragging anything, I just cut it. Okay? If I just cut that string, there's a 0.098 newton force acting on a 10-gram mass. If I take 0.098 newtons and divide that by 10 grams, I'm going to get an acceleration of 9.8 meters per second squared. Okay? Now, the reason I don't get an acceleration of 9.8 meters per second squared is because I'm dragging this cart that has a 500-gram mass and a 20-gram mass stacked up here. So, the applied force acting downward is going to be 0.098 newtons. So, the more mass that I have to drag, obviously, the smaller the acceleration is going to be. So at the end of the day, to calculate this acceleration, you're going to go force net divided by mass equals acceleration. Now, here's what you want to think through. You want to think through this algorithm, okay? And go, how did I calculate net force? That's the weight of what's ever hanging from the end of the string. That's going to be mg. So this is going to be some mass that's hanging times your gravitational acceleration. Okay? Now, which mass do you use here? The mass that's on the cart, or the mass on the end of the string, or the combined mass?
Combined.
Combined mass. You always, listen to me, you always divide by the combined mass. Because every particle of mass, every proton, electron, neutron, has mass. It wants to remain at rest. And it's always going to remain at rest until an outside force acts upon it. So this is why you have to divide by the combined mass. What typically people screw this up is they just divide by the mass that's up there on the cart. Okay, that's on the, no. That force is making that 10 kilogram mass just the same way that it's making that cart move. Now, what some people like to think of this in terms of like another perspective is that imagine that I have that cart and I put a fan cart on it, and that combined mass is about 1 kilogram, which I'm guessing is what your combined mass is. Okay? So if I have that combined mass sitting up there on the cart, and I have a fan that can produce 0.098 newtons, I could find my acceleration by taking 0.098 newtons, dividing it by the combined mass, and getting that acceleration. So the reason that we use weights on the end of strings to do this is because that produces a very exact amount of force. I know when I take a 10-gram mass and hang that from the end of a string, I know I'm going to generate exactly 0.098 newtons of force. I don't have to worry about, is my battery running down? Are the bearings going out on the fan? Which speed do I have the fan on? Is the fan pointing in the right direction? I don't have to worry about any of that. So by suspending that 10-gram mass, I generate an exact amount of force I know exactly what that value is, and then I can calculate my acceleration. So, then we're going to swap that out. Then we're going to take a 20 gram mass, and we're going to put that on the end of the string. Now look what's going to happen. And this is one of the most critical things you have to get. Listen to me. We're going to revisit this later once we get more into gravity. Now I'm going to have a 0.196 Newton force. Okay? I've doubled my force. So here's the deal. Again, you need to look at this in two situations. Situation number one, I've got the 20 gram mass. I cut the string. I have a 0.196 Newton force acting on a 20 gram mass. And if I take 0.196 and divide that by 0.2 or 0.02 kilograms, I'm going to get 9.8 meters per second squared. So this is the most vital thing. If I just cut the string, I got a 10 gram, I got a 20 gram. They both end up with the same acceleration. But here's the most common misconception. And these are these questions that I asked you on the next page. I end up with the same acceleration, but do not tell me, oh, gravity is the same for both of them. It's not, okay? That 20 gram mass has twice the force acting on it as the 10 gram mass does, okay? Twice the force. But it also has twice the mass. Therefore, it has twice the inertia. So I have to have more force acting on more mass when it's falling to get the same acceleration. Because if the same force acted on everything, I wouldn't get the same amount of acceleration. So what I want you to see is that when you cut something and it's in free fall, the amount of force is proportional to the mass. More mass, more force, more inertia, but I get the same acceleration. Okay? So that's why every one of those questions on, where's it at? Yeah, on page 4, on that 10, every one of those statements is patently false. Okay? There isn't a single question on page 4, question number 10, that is true. Now, don't get hung up on like 10C where it says, and my favorite gravity G is negative 9.8 meters per second. Go, oh, that's false because it could be positive. Okay? No, that's not what makes it false. Okay? That is not what makes it false. You can say gravity causes an acceleration. Okay? That's cool, right? But you cannot say gravity is negative 9.8 meters per second squared. That's just the effect of the gravitational field. Okay? All right. So when you get down to question number 11, let's say you get to number 11 and you go, man, I have no idea how to do this problem. I am screwed. Okay? Look.
That was a sarcastic question. I thought it was just asking what his favorite gravity was.
What?
I thought I was asking what your favorite gravity was. I said false. On the moon you can dunk, but I thought it was like, and is my favorite gravity negative 9.8 meters per second? So I was like, nah, the moon would be kind of cool. So I said false.
That's an extra point.
Louis, I got to give you credit.
I read it weird.
Louis, I don't know. For decades, ever since I started teaching physics, I realized that's been a misconception. Okay, so on 2 continents, almost over 30 years, I have never had a kid interpret that question that way. Never. So that's a shout out to you, Louis.
Oh, I'll take that.
Take that. I mean, seriously. Two continents, probably. I don't know how many thousands of kids I've taught. No one's ever interpreted that question that way.
I was tired and I was reading it. I was like, he just asked us what his favorite gravity is. I was like, oh, okay. So that's wrong.
No, it's. So here, let me tell you a story.
I'll leave it on there.
So you know, as a teacher, when you write questions, in your mind, you think this is how the question, how the kid's going to ask the question, okay, and how they're going to interpret it, and this is how they're going to answer it, right? So you write a question in your mind, you know what the answer is going to be. Oh, this is where I want them to end up. So, and we'll study atmospheric pressure eventually, but atmospheric pressure changes depending upon your height, and it's a linear function, okay? So the higher you go, the less atmospheric pressure that there is. So this is why when you go to, like, if you fly in a plane and you drive to Colorado, up in the mountains, your ears pop, okay, because of the pressure differential. So the physics teacher wrote this question, and he had just got done studying atmospheric pressure. And so the question is, he gives this question to the kids, and he goes, how could you use a barometer to determine the height of a building? And so in his mind, he's going, you measure the atmospheric pressure at the bottom, you climb to the top of the building, you measure the atmospheric pressure there, and the difference between those atmospheric pressures you would use to find the height of the building. Okay, so in his mind, that's how it's going to play out. So one kid said, well, I'm going to climb to the top of the building, I'm going to drop the barometer, I'm going to measure how long it takes for it to smash on the ground, and knowing how long it takes for it to fall, I'm going to figure out the height of the building. Okay? One option. Another kid wrote, I'm going to find the superintendent of the building. I'm going to go, hey, I'm going to give you this really nice barometer if you tell me how high the building is. So, in both situations, they use the barometer to find the height of the building. Two completely different applications, but that's why when you write a question, you always think, oh,
how can this be skewed?
yeah, well, no, that one, I never thought of how that one's going to get skewed. Okay. So, when you get to question number 11, okay, think through the process. Go back to the beginning of this section. How did you find the net force? Oh, I took the mass of what's hanging from the end of the string times 9.8 meters per second squared. Oh, then what did I do? Oh, then I divided by the combined mass. So if you can figure out that algorithm or that thought process on how you did that at the beginning of the lab, you can apply that algorithm to the situation later on. Okay? All right. Really, I'm gonna be laughing about that all day. Anyway, anything you want me to go over on the lab? That acceleration on number 11 would make a not so good GPA. Not horrible, but not so good.
What? The contact force and the long force?
Yeah.
Is
So
that-
long range force would be a situation where it doesn't have, where you're not in direct contact.
So gravity.
Gravity.
Right.
Okay. Anything else? Going once? Going twice? So staple your graphs to the back and get those handed in. So, Vitor. Group. Okay. So today we're going to have a couple of demonstrations of Newton's laws of motion. Okay? So the first one, we have the yonder bed of nails, which was built many, many years ago. It's actually, there's about 100 pounds of nails in it. And it took forever because you had to like pre-drill every hole and then pound the nails through it. A kid by the name of Jeff Weisenbach built it. That was like his spring project. It took, I don't know how many hours he spent drilling holes and pounding nails. But anyway, so it's a cool deal. So here's what's going to happen. Is that I'm going to lay on the bed of nails. I'm going to take a concrete block, put that on my chest, and then I'm going to have Louie take the sledgehammer and smash the concrete block while it's on my chest. Okay? That's why I said,
Yeah.
hopefully,
We're confident.
You're
Confident.
good?
Yeah, we're confident.
pretty big targets. Okay? So let's look at this from Newton's 3 laws of motion, right? So my body has a certain amount of mass, probably more than it should, too many Big Macs, but oh well, it's the reality. And the concrete block has a certain amount of mass, it has a certain inertia. And the sledgehammer, when it's coming through, has a certain amount of inertia, okay? So the sledgehammer wants to keep going, but my body wants to remain at rest, okay? So my body wants to remain at rest, the sledgehammer wants to keep moving, okay? That's the inertia side of it. Now, let's jump down to the third law. Okay, for every action there is a reaction. For every force there is an equal and opposite force. Okay, forces are coupled. There's a whole bunch of different ways you can talk about this. So if you define, here's the surface of the block. If you define down as being a negative value, okay, so the sledgehammer is going to exert a negative force on me. So by Newton's third law, what's the block going to do? It's going to exert an equal and opposite positive force pointing upward. Okay? That's what's going to happen. I'm going to have a negative force, I'm going to have a positive force. Okay? Those forces are coupled. Okay? That's going to be important. Now we're going to jump to the second law, which is F equals ma. Now think very carefully before you answer this. When Louis hits me with that sledgehammer, do I want the sledgehammer to accelerate when he hits me?
Yes.
No. Yes.
I pray that it
Yeah,
accelerates.
okay, yeah.
Hopefully it doesn't go through.
Because if it doesn't accelerate, what's going to happen?
It's gonna go through you.
It's going to keep going at a constant velocity into my chest. That's not going to end well. Okay? Somebody run down to the nurse, get some ice chips and saltines. Okay? It's like, what happened? I don't know, there's sledgehammer broke in the chest. We're going to get some ice chips. Okay? So I want that sledgehammer to accelerate. I'm going to accelerate. But which one do I want to have a larger acceleration? Me or the sledgehammer?
Sledgehammer.
I want the sledgehammer to have a big acceleration. Okay? I want to have a small acceleration. Because if I have a large acceleration, bad things are going to happen. Okay? So it boils down to this. The forces on the sledgehammer and me are going to be the same. Newton's third law. The block and I are going to have a relatively large mass. So I want to have a small acceleration. I want the sledgehammer, which has to have a big acceleration. Okay? That's what I'm banking on. Notice that Newton's third law doesn't say accelerations are equal and opposite. Okay? I wouldn't do this demonstration if that was Newton's third law. Okay? Forces are equal and opposite. Okay? Got that idea? Okay. Louis, are you ready?
Mm-hmm.
Okay. If you want to get your phones, in case something goes south, we have this on video.
World star.
Louis, are you not nervous, bro?
Actually, I need somebody to record it on my phone.
I have full trust.
You have full trust in yourself.
No more touch. Pop, am I right?
So,
What?
Am I right?
is
Right, you just
that
pop
just
in
the
it.
total mass?
weight. Oh, okay.
I go down. or I'll
Total
go down.
accelerated
I'm
total mass.
confident. I'm confident I did it right.
And then these two, you don't know how to find.
Because these look pretty good.
Well,
Like they look
I'm
pretty
still
good.
doing it.
Okay. I'm gonna just do it for
Okay.
here.
Oh my god, we actually got a bed of nails.
Hey, did you check these?
Yeah.
Yes? Yes?
Yeah.
Yes. Hey, hold on.
Wait. Is that what you got?
You did it right.
Okay, grab yonder block.
Okay.
Oh
Pop.
my God.
Wait.
How'd you get the?
Lay down flat this way. Nope,
Other way.
nope, 90 degrees.
With the flat side.
Flat side.
Yeah,
There you go, yeah. No, perfect, there you go.
yeah. That way.
There you go.
No way, Louis, actually.
Okay. I'm trying to
Do you
talk.
want me to wear the mask or do you want to wear
No, oh, no, okay, yeah, I'll wear the mask. Okay. I want you to be able to see. Okay. I want you to be able to see. Okay,
Just
So-
keep my eye.
yeah, just close your eyes. So, yeah, this isn't, so, it's like trying to talk with an elephant in your chest. So, Louis gonna come down, he's gonna apply negative force, right? I want the block to exert a positive force. I want the sledgehammer to accelerate. I want to have a minimum amount of acceleration, okay? You got this?
Yeah, I got it.
Okay, now, you're not trying to ring the bell at the carnival,
Uh-huh.
but you can do like a pretty good half to three-quarter swing,
Okay.
okay? I actually want you to hit it hard enough to shatter it, because if you don't hit it hard enough to break it, then all that energy gets transferred directly into my chest. Okay.
He gets hurt.
So, so it's actually
So-
less painful for me
Would
if
you?
it breaks. You wanna hit it right in the middle.
Louis, get
Okay, right in the middle.
You wanna try and hit it right in the middle of this scene.
Okay, cool.
So just, boom, right there.
Alright, do you want me to go from the side or?
Yeah, whatever.
You should probably move the desk.
I'm going to. Okay.
Oh, you got it.
Yeah, use the domain. Let's make sure we're going with the domain, okay?
I
Just thought I'd point that out.
have this much trust.
I have this much trust in you.
I have this much trust in myself as well.
Okay, you do?
You're in safe hands.
Okay, great, okay. I'm not worried about your hands, I'm worried about the sledgehammer. Okay, you ready?
Yeah.
Okay, you want to practice one or you good?
I'll give it one practice.
Okay, all right.
Where would I?
Well, I mean, just kind of, get a feel.
On the table.
Okay.
Yeah.
Okay, good. All right, you ready?
Yeah.
Okay, let's do this. Ready?
Yeah.
Okay. Do it.
Is that a good one?
That was a good one.
Let me get a couple of these.
Hey, he's not
Okay.
alive.
Wow. That was a good one. Yeah. All right.
My turn.
No.
Does that hurt?
Yeah, it does. That hurts a little bit. Yeah.
I
I
can.
want to try.
Oh.
Okay, help
You
me.
can swing the brick. The brick in my chest.
Okay. Woo. Woo. Okay.
Wow. Good swing.
That was a good one.
No, wait till honors physics goes around. You gotta do it 4 classes in a row.
Yeah. Well, that's why it's nice to kind of space that out, because otherwise you do it like 3 times. One time I had to do it like 3 times in a day. Oh, I was tired of these things.
You just bring the,
Well, yeah, you wouldn't want
Huh?
to.
you just bring this to school.
Okay, now, come back over here. So, you should record that? Yeah. Okay, I'm done. I'm done.
No.
You're selling.
Okay,
And it's online.
okay. All right, well, grab.
No one recorded. I didn't.
We gotta do it again.
No, I don't have any more blocks.
We got half of a block. We got like 6 halves actually.
No, I'm not gonna lay that flat. No. Okay, Vitor, can you go grab yonder camera?
Yeah, grab the real thing.
Yeah.
Yeah, grab the real camera.
Get the camera before.
I'm doing.
That was crazy. Did you record? My bad.
X-Men.
Okay.
That could have gone so
Vitor,
strong.
we good?
Yeah, we're good.
Okay.
Oh.
Is this
That was
the
good.
long one?
So, I situations. So let's look at something simple. So let's say you have a car going 12 meters per second, and you're going to hit the brakes, and the car is going to come to a stop, okay? And let's say that took, 3 seconds. And the car has a mass of 10 kilograms, okay? Does that provide you enough information to calculate the force that's acting on the car? Okay, well, let's look at the car. Car's moving, and then we're going to bring it to a rest. So what are the three forces acting on the car?
Gravity,
Gravity's pulling it down, right?
Normal force.
normal force,
The normal force is
Pulling it.
provided by the road, and then you have
friction.
some frictional force, right? Okay? Since I'm asking you to calculate an acceleration, what are the forces not going to add up to? Zero. Okay, that's going to be a key thing. So right away, just find your acceleration. This is why you have to be able to do acceleration before you do forces. Okay, that's why it has to go in that sequence. So, if you want to go v naught dat, if you want to go old school, initial velocity, 12 meters per second. Final velocity, 0. Distance, don't care. Acceleration is what I don't know. Time is going to be 3 seconds, right? So at this point, do I have enough information to calculate the acceleration?
Yes.
What can I do?
Can do V equals V naught plus AT.
So I can do V equals V naught plus AT. My acceleration is going to be V minus V naught over time, right? So I'm going to show you two different ways you can do this problem. It just depends upon what you feel comfortable with. One option is that you find the acceleration by itself. So you can take 0 minus 12 meters per second divided by a time of 3 seconds and get an acceleration of negative 4 meters per second squared. Okay? So if you like to divide and conquer, find your acceleration. Then you want to find the force. Force equals mass times acceleration. So that's going to be that mass of, 10 kilograms? So that's going to be 10 kilograms times an acceleration of 4 meters per second squared. I'm going to get a force of negative 40 newtons. Okay? If you like to work this problem in sequences, that's cool. If you want to work it in kind of one big idea, you can go, F equals ma. But my acceleration is going to be V minus V naught over time. And then you can just take 10 kilograms times 0 minus 12 meters per second divided by, what was the time? 3 seconds. So you can either work it as just one big F equals ma problem, or you can find the acceleration separately, multiply that by the mass, get that. So this would be my frictional force, right? Because that's what's making it stop. So I have a frictional force of negative 40 newtons. That's what's making this thing slow down. Now, the other thing that I could do is I could reverse this. I could say a car is moving. It has a frictional force of negative 40 newtons. Mass is 10 kilograms. Find the acceleration. So if I flip this and said, here's the force, here's the mass, find the acceleration. Then you take those 10 newtons, divide that by 10 kilograms. I get an acceleration of negative 4 meters per second squared. Then I could use that to find the final velocity, initial velocity, something like that. Okay? So depending upon which way you want to make the door swing, those are your options. Okay, so stop that for a second. This multiple choice question number 5. Okay? And again, answers on the left, work on the right. You treat this as like a page out of a notebook, okay? Or out of a textbook. And yes, there are some questions out of your textbook as well. So let's talk about question number 5. So I say if with no force, a force F results in an acceleration A when acting on mass M, then tripling the mass and increasing the force 6-fold will result in an acceleration of blank. Now, you're tempted to read this and go, oh my God, I have no idea what this is. It's like I'm reading a foreign language, okay? I'm going to show you 2 ways that you can do this problem, okay? One is the elegant, the other one is smash mouth, okay? So one option is you go, well, here's my relationship. F equals MA. So let's say you like numbers. It's like, Brickham, I see better with numbers, and some people do, and that's cool, okay? So what's a simple force that you could pick? 1 Newton. That's as easy as it gets. What mass do you want to use?
1 kilogram.
1 kilogram. What acceleration do you want to use?
1
meter per second squared. And that's how 1 Newton is defined. 1 Newton is defined as the force needed to take a 1 kilogram mass and make it accelerate at 1 meter per second squared. Okay, that's how 1 Newton is defined. Okay? Now, that's my initial set of conditions. Now, then we're going to change it. I'm going to say, I'm going to triple the mass. So instead of 1 kilogram, I'm going to have 3 kilograms. Okay? I'm going to increase the force by 6-fold. So instead of 1 Newton, I'm going to have 6 Newtons. So what does my acceleration have to become?
2.
2 meters per second squared. So my acceleration will
Increase.
double, right? It's going to go from 1 meter per second squared to 6, or to 2. So if you like numbers, okay, it's like Burkamp, I'm very concrete. I want to see numbers. Fine, make up numbers. Now, the more elegant mathematical approach is to go, okay, I can play this game. F equals ma. What are you going to do with the mass?
Multiply by 3.
So that's going to become 3m, right? What's going to happen to your force?
6.
It's going to become 6F, so to balance everything out, I have to have 2A. Okay? I don't care how you think through this. Okay? It makes me no difference. If you like the elegant mathematical approach, go with that. If you go, Burkamp, I want numbers. Fine, make up numbers. Okay? It doesn't make me any difference. Okay? Now, on like problem number 1, I want you just to reinforce, I want to reinforce this idea. When I am talking weight, weight is a measure of force based upon a gravitational field, and that's going to be in newtons. If I want mass, I'm going to say mass. That's going to be in kilograms. So on problem number 1, when I say compute the weight of the following on Earth, 0.51, I want a value in newtons. And don't worry about making those negative, okay? I just want numbers, all right? That's all I want. Then you're going to draw a graph with mass on the x-axis, weight on the y-axis, okay? And if you want to do that on graph paper, you can. If you just want to make that off to the side, but this graph has to be pretty much on scale. This can't be just like a random numbers. This thing, to really see this, it really has to be a specific value. When you get to question number 4, so visualize this, or problem number 4, I should say. Here's this scale, and you have a 500 gram mass sitting on the scale. The scale measures in newtons, okay? Okay, there's a scale measured in newtons. What I'm asking you is that if you take a 500 gram mass and set it on that scale, what should the reading in newtons be? Okay, and again, don't worry about making it positive, negative, just give me the number, okay? Now, what's happening on question C is that I'm going to take a balloon filled with helium and I'm going to tie that to the balloon. Okay, so imagine I've got this balloon tied to it. And then the scale drops to 4.8 newtons, okay, because the balloon's providing some of that upward force, okay? Keep in mind, as long as that mass isn't accelerating, that all of the forces have to add up to 0. So in this situation, you're going to have some downward forces, you're going to have some upward forces. So in this situation, because everything has to add up to equal to 0, this is where it would be beneficial to make that weight be negative value. And then define your upward forces, the balloon, the force on the scale, make those be positive values, okay? Because you want everything to add up to equal to 0. So here's the difference. On problem number 1, I'm just asking you to calculate the values. Don't worry about making them negative. But when you get to a question like number 4, where everything, you're gonna have to draw vectors and it's gonna be acting up and down, that's where you wanna worry about making things positive and negative, okay? Anyway, you're on your own. Be free. So, Vitor,